All right, thanks everyone for coming. Sorry for the short delay, but we're very happy today to be joined by Dr. Brittany Miles. She got her PhD last year at University of California, Santa Cruz, where she racked up a number of graduate fellowships and awards, including the NSF one and others, before moving to the University of Arizona, where she's now a 51 Peg B fellow and a presidential postdoctoral fellow. So recently, Brittany's been working on the mid-infrared, looking at very cool brown dwarfs and exoplanets, and we'll hear about that and the exciting work she's been doing with JWST, I'm sure. But before that, she also worked in the UV, so she really spans from 0.2 to 10 microns or something in her work, and also worked on characterizing near-infrared detectors that could be useful for ground-based exoplanet studies. So that's quite a wide range, and we're very pleased to have you here. And also, as you know, Brittany will be here today and tomorrow, so plenty of time to meet. Take it away.
Thank you. So the title of my work is mainly about characterizing brown dwarfs and directly imaged exoplanets in the mid-infrared. My abstract was a little vague, but I decided to have a little more depth focusing on where we're going with JWST and brown dwarfs rather than my instrumentation work. So I just wanted to take a step back on what direct imaging is, where are we at in terms of actually measuring the thermal emission from planets around other stars. So this is the HR 8799 planetary system. It's like the stereotypical image people think of when you talk about taking a picture of a planetary system around another star. And so this technique allows us to actually emit or detect the heat that these planets have left over from their formation, so that these images also provide information on the flux, and you can tie that back to a luminosity curve to figure out how massive these objects are and other things like that. So how is this observational technique limiting? So this is the same image with the orbit of Neptune plotted. So all of these 4 planets are typically very far out from their host star compared to other planets in our own solar system. And so to date, direct imaging is primarily biased towards really young systems. So they're young, they have a lot of heat from formation, and they're very far out, so they're not competing with light or residuals from the host star in the center. And so where do we want to go in the future with JWST and 30-meter class telescopes is actually going into not just photometry, but actually getting low resolution spectroscopy from these planets. We want to know, what kind of clouds are in these atmospheres, what kind of molecules make up the atmosphere, how's that tied to where they formed in the disk, and how they'll evolve over time. And the second bullet point is mainly for ground-based telescopes. We want to access other planet classes. So a lot of the directly imaged exoplanets we know about today are these really massive Jupiter-like planets. So even the more recent one that's been discovered, LEP-B, I believe, it's Jupiter mass, but it's so massive that it's thousands of kelvins. And so we need to actually figure out, how do we access things like our own Earth? How do we go to sub-Neptunes and things like that? So this slide is to motivate why we need to study brown dwarfs to better understand gas giant exoplanets and understand, how do we optimize our instruments to get the best information to understand their atmospheres. So this is an HR diagram. The y-axis is just the J-band magnitude, which is a proxy for effective temperature, plotted against the J minus K colors here. So these orange circles are photometry points from brown dwarfs. The blue points are data points from directly imaged exoplanets. And so both brown dwarfs and gas giant exoplanets are basically just hydrogen balls that collapse over time and they get cold, and whatever molecules are there, they're what you'll see in a spectrum. And so you can typically look at a similar temperature brown dwarf to understand what you'll see on a gas giant planet that's very far from its host star. And also brown dwarfs are easier to study because they're typically either very far from a companion or just completely isolated. So they're accessible to slit spectroscopy, and from the ground, you can easily get high signal to noise data. And with JWST, you can also get signal to noises of hundreds in just less than an hour. And lastly, you'll notice that directly imaged exoplanets typically have this cutoff at this cutoff is about 600 Kelvin or so at like a J band magnitude of like 16. But the brown dwarf sequence completely covers this large effective temperature range where we don't have any directly imaged exoplanets right now. So you can observe these late T and early Y dwarfs to kind of figure out, okay, once we improve our instruments, get to 30-meter class telescopes, how will these cold exoplanets look like? What wavelengths, what resolutions do we need to, detect things like methane, carbon monoxide, et cetera, et cetera. And lastly, we're going into why the mid-infrared specifically is important for these efforts. So this is a plot by Zach Briesmeister showing, so on the left, I'm focusing on this one, it shows the actual flux within a specific bandpass compared to the overall luminosity of the object or the overall flux. And so on the x-axis, you have effective temperature going from hot to cold, and the 1 to 2 microns region is effective for getting the overall luminosity of things that are above 600 Kelvin, or maybe like 800 Kelvin, but you really need the 3 to 5 micron range to actually get a better flux budget to understand what is the actual heat from this object. And the black lines on both plots are just showing kind of what's the coldest exoplanet we've detected so far. And this arrow just represents where we need to be in the future. And instead of just using the numerical notch filters, these are actual infrared filters people know about, JHLKM. L band is 3 to 5 microns, M band is 4.5 to 5 microns. And so even in these standard bands, you would really want to be in the mid-infrared to detect these planets. And I don't know what that was. I don't have time to go into all what opacities we expect to exist, but carbon monoxide, carbon dioxide, phosphine, germane, these have been detected in Jupiter and Saturn, all have very strong opacities between 3 to 5 microns. And it's important to go beyond just carbon-based and oxygen-based molecules to get an accurate budget saying is this object just have a weird C/O ratio, or is this metallicity weird? So actually tracking other molecules is crucial to understanding how they form as well. And lastly, I won't talk about a specific project, but this is just part of my postdoctoral research plan, is detecting and characterizing planets from 8 to 13 microns. And so this is a plot showing the contrast. The higher the value, the easier something is to detect compared to its host companion. And on the x-axis is just wavelength. So this green line is a 400K brown dwarf model. And on the bottom, I have a cloudy Earth atmosphere. And so here I'm highlighting the 1 to 2 micron region and highlighting the 8 to 13 micron region. So for Earth-like planets, the contrast ratio to a solar type star is hundreds to 1,000 times brighter at the mid-infrared compared to the optical. This does not mean we need to abandon all optical efforts. It's just saying in terms of for detecting and the hope of doing spectroscopy, you want to go in the wavelength where Earth-like planets are the brightest. And also here, brown dwarfs or gas giants, which we know exist, also have significant emission at the longer wavelengths. And this feature here is ammonia, which I'll show a little bit in the next slide. So this is a spectrum of an Earth-like planet at different resolutions. And this is the ozone feature. It's a biosignature. And so I'm just showing at different resolutions, R of 25 all the way up to R of 2000. And this is, so I've done calculations, if you had just put the LBT on a 30-meter telescope, how well would you be able to see this feature? And you can see ozone in about 100 hours or so. And so we need to think about how that's actually going to happen with the optics and mechanical design, but that's something I'm interested in studying with my postdoc. And for brown dwarfs, this is Spitzer data. People have seen this feature with JWST, it's just not published. It's just not published yet. But from 8 to 14 micron, so this is they use a spectral type, but I'm just saying the effective temperature is about 1,000 Kelvin. You could see ammonia absorption features, and also this slope right here is carved out by methane. And so you have extra detection of the molecules, or you have the potential for extra molecular detections from 8 to 13 micron for brown dwarfs. Yeah. Thank you. Okay, so just an overview of what I'm going to talk about today and what I'm working on as a postdoc. The first thing I'll talk about is the complete 1 to 20 micron spectrum of VHS 1256b. It's about 1,000 Kelvin brown dwarf, and we studied it for one of the JWST ERS programs. And the next project I'm talking about very late T and early Y dwarfs. So these brown dwarfs that are in the temperature regime where we haven't detected gas giants just yet. And I'll show how CO absorption can also track atmospheric mixing in gas giant exoplanets. And lastly, we can talk about this in a meeting if you sign up with me. We need to understand which mid-infrared detectors are adequate for imaging and spectroscopy of Earth-like planets and other things in the mid-infrared. Okay. So the point of the early release science programs for JWST is to understand how well can JWST do important science for our community. And so for the direct imaging team, we chose one target for near-spec IFU spectroscopy and also MIRI IFU spectroscopy. And people ask, why do we pick this target? One, because the GTO teams picked all of the good ones before and there's not that many left. This one is fairly far. It's not image well here, but it's a M-dwarf binary companions here, and VHS 1256b is also very far. So it's accessible to, it's basically a point source in most spectroscopic modes. And also it has the same photometry as HRD 799D here. So from low resolution spectroscopy and near infrared photometry, these objects are fairly similar. And so we want to get a high quality spectrum of this to kind of figure out what you should expect here in the future. And we got spectrum that are about an R of 1700 to 3000. The data covers 1 to 28 microns, but the fourth channel of MIRI is very dim. So we really only have 1 to 20 microns. Okay. So before I show the spectrum, I'm just going to show, what's kind of the best you can do from the ground so far with Spitzer. And typically getting a spectrum from like 1 to 2 microns is pretty standard on most observatories. You can get like a signal to noise of 10s to even 50 on a brown dwarf. 3 to 4 microns is a little hard. You can get something that's, you can see the slope, but it's very hard to get the telluric calibrations right. And a lot of people just don't try to get 4 to 5 microns on the ground because it's difficult. And then Spitzer kind of filled in this mid-infrared, this longer mid-infrared regime at like an R of 90, but the signal to noise is also really low. Okay. So this is the spectrum of JWST. It's kind of like the state of the art of what you can do right now to get a complete spectrum of a brown dwarf. So the past slide, the data cut off at 10 microns, but now we can get out to like 20 microns. So with JWST alone, we've effectively doubled the wavelength coverage that you can get on a planetary mass object. And this, this is accepted. Also, my code is on GitHub. And I guess just to talk about how some of the challenges with this. So there was no proprietary period when this ERS data came out, and it was pretty rough doing some of the calibrations last July. So the near spec data covers 1 to 5 microns. So for every filter grading combination, I use the default JWST pipeline, but I also had to reduce the commissioning A-star data to actually calibrate each filter grading combination to get this spectrum to look like this. MIRI had a MIRI, which is like 5 to 20 microns, worked pretty well out the box. And so we didn't have to do too many offsets for that one. But thankfully, there was significant overlap between the wavelength regions where near spec and MIRI overlap. So I was really happy with that and felt validated by that fact in the paper. And so MIRI, one of the challenges with that, there's fringing in some of the spectroscopy. So we had to do some sine wave fitting to get some of those out. But I think there is some room for growth in terms of that data reduction for things that have significant molecular features. So this is not the final, this is just one iteration that got published. So the community got to it and you know how much signal to noise you get. But I think there's development to be done. And I'm hoping people actually interact with these data products in the pipeline we have out. Okay, so now the fun part is actually what are these spectral features? What can we see? So you can see a few alkali metals and also water. So we're starting at 1 micron. You have sodium and potassium doublets here and these very nice features. You have a very nice obvious water feature that from the ground will be, there would basically be like telluric scatter here. And so you have very clear detections of water in this brown dwarf at good signal to noise. And just for like an empirical comparison, you know, how does this object compare with other standard brown dwarfs? So on the bottom, we have the spectrum of VHS 1256b, and we have an L6, L8, and a T2. So these brown dwarfs have very broad, or they're not broad, but they're very deep. That's because they have very high surface gravities. The features for VHS 1256b are fairly shallow, so this indicates that it's a very low surface gravity brown dwarf, which is consistent with it being young and its atmosphere or its radius not collapsing all the way. So the next step portion of the spectrum, 1 to like 1.8 to 3 microns, you have more water. You have carbon monoxide and also water here. You can see where some of the artifacts of the data reduction pipeline show up in the spectrum, where you have these wobbles here. I've been working on another iteration of this, but this CO feature still holds up in feature reductions. But I think these wobble features are an artifact of going from the detector image to an interpolated like IFU cube that you see. The next one, this is 3 to 4 microns, and you have a very obvious methane feature here. So on the top, I have the opacity curve of methane plotted at the right appropriate pressure and temperature. Wherever there's a peak in methane, you should see a dip in the spectrum. And so this dip here in 3 microns corresponds to this feature right here. And I'm just going to do some comparisons with other similar temperature brown dwarfs. So this is an L5, it's about 1700 Kelvin, 1500 Kelvin, 1500 Kelvin, because spectral type does not always correlate with effective temperature, that's why it's like that, and 1000 Kelvin, which is a T5. So this brown dwarf is about 1100 Kelvin. That means it should have a very large methane absorption feature here, but its methane feature is also very shallow, as if it were more like an L5. And so this is evidence of the apparent abundance is thrown off by disequilibrium chemistry, which is driven by atmospheric mixing. So this feature of methane, so okay, let me just take a few steps back. Brown dwarfs of this temperature typically have a methane-dominated upper atmosphere, and deeper at higher pressures and temperatures, you have carbon monoxide gas. And so if the mixing through the column of the atmosphere is much faster than the rate carbon monoxide converts back into methane, you'll have a lower apparent methane abundance in this spectrum. And so that's what we see here. And this is just a comparison of 1 hour Keck versus 20 minutes of JWST. So I actually took this data of this object right when I started grad school. And this is the same wavelength region. It's just that because there's so much, like there's low transmission, and also the lines vary. Precipitable water affects how you reduce the spectrum. And so this methane feature is very hard to see from the ground, but very obvious to see with JWST in less time. Yes. Okay, and this is my favorite feature. This is carbon monoxide. So on the top, we have the opacity of carbon monoxide plotted. Again, where you have a peak, there should be a dip. And it basically looks like a model. And you have these really nice cone features of carbon monoxide, and this is the best CO feature I've seen so far on a brown dwarf. There's a lot more. You can write a whole paper on this because we're kind of rushed with the timescales of things. I think there's more work to be done on, like, you know, can you infer anything about the PT profile and how this shows up compared to the actual opacity that's there? And also, there's evidence of carbon dioxide. There's evidence of carbon dioxide at 4.2 microns, where we made a brown dwarf model where we included CO2 and removed it. But because we were on the struggle bus trying to fit the entire spectrum, it's hard to actually, it's until someone figures out how do you fit 1 to 20 microns on a brown dwarf, these secondary, less obvious molecular features are going to be tentative for the time being.
Perfect.
Yeah.
So, several slides ago, I think you mentioned basically this source is very young, right? And so I guess because I don't work on this, I'd love to know just roughly the inferences you're making about the mixing,
Yeah.
does that correspond as in an expected way with the youth of the object?
So yeah, so basically you start with a brown dwarf, and as it cools over time, its radius also shrinks. So there's more mass in a smaller area. And so over time, you would expect like either mixing to kind of slow down because there's more surface gravity inhibiting it. So it is consistent with, I would say there isn't a lot of published work on it, but if you plot theoretical models, I think it follows that expectation. Yeah, and I have another plot to talk about that later on. So for the MIRI data, here we have this is like 6 to 18 microns. I think, so one, these are the major expected absorbers across this wavelength region. So we have water, methane, and also water across these wavelength regions. And also one of the most important features here is actually this detection of like a silicate cloud feature around 10 microns. I think a visual comparison would make that a little more obvious. So here in gray, it's the JWST data with the resolution knockdown compared to two different brown dwarfs, where you have a cloudless brown dwarf here, where the spectrum is just a slanted line. And for the cloudy brown dwarf, you have a silicate feature here where there's a slight depression here. And so empirically, we know there is some kind of silicate feature in this brown dwarf to say like what size particles or where are they along the PT profile. I think that's going to take more work. And so this kind of detection is important because we know brown dwarfs are variable. You know, we want to know, is that variability due to clouds, patchy clouds coming in and out of our line of sight? Is it due to temperature variations? So actually having the silicate cloud detection is important for informing those models that for the atmosphere. Yeah.
What was the time baseline of the observation?
So I believe it was less than like 10 hours. They're pretty like contemporaneous. And then also part of the ERS team did a large ground-based variability study. So we actually tracked, you know, how variable is this object over what time scales. And we got pretty lucky because we were in a variability lull for this object. And so I think that is to be seen on, you know, does that matter for other programs that do time series stuff? So this is atmospheric modeling, still very much a work in progress, but this is our best effort. The black line is the data for VHS 1206b, and then the red line is our best effort model. So the effective temperature is about like 1100 Kelvin. We have a fairly low surface gravity. I believe that's like a log G of like 3 or something, but I have to check. And we had to utilize a 2-cloud model where we have a very thin, we had the upper cloud was like this very thin silicate cloud, and we had to use a deeper, thick cloud to actually match the overall SED of this object. The big issue, as you can obviously see, we can match the general shape. We cannot match like the CO feature. We can't match, I don't know how we match some of these neutral gases, but it's by adding clouds, we basically wash out every single like meaningful feature here. And so I think there is going to be more work to actually approach this from a forward model approach and also with atmospheric retrievals. Yes.
Yeah,
Like, what is the major absorber contributing to each one? So that's a good question. I'm not sure, like, if you took every molecule out, what's the biggest contributor to, like, you know, the SED, right? I don't think outside of like a black body, I'm not sure what that molecule is. There's some from like hydrogen, that's the biggest thing there, but I couldn't tell you what exact shape that had. I got you. That's a good point. So outside of hydrogen and water, I'm not sure if there is a feature that extends over many wavelengths that contributes to the overall like heat of the object. Is that what you mean?
Yeah, like in the sun, you know, you get the fact that it's minuses, so something like that.
I got you. That's something I could look into. Gwen?
Yeah, I'm curious. So the cloud models, do they assume that like the entire surface is covered in clouds, or are they patchy? So there are clear lines of sight and then other lines of sight that are looking through the clouds.
So for the models we use, it is definitely assumed that it's like an entire like coverage of the object. And the way the kind of like cheat code is that you take combinations, but that's not like actually taking one cloud here, one cloud there, and doing radial transfer properly. But I think there is room for that. Yeah. Yeah. Okay, we're at like 30 minutes. Okay. So conclusions of this is that VHS 1256b is a fairly young, cloudy planetary mass companion with an atmosphere that's out of chemical equilibrium. This has implications for directly imaged exoplanets that are, have the same photometric properties, that they likely also have their atmospheres out of chemical equilibrium, and we have to be able to consider atmospheric clouds when modeling them. And JWST has the capability to characterize other brown dwarfs with a signal to noise of 10 to 400 at medium resolution. This is I cannot stress this enough as like someone who was a grad student looking at Spitzer data. Like, we kind of need to use this telescope now before it's down. It's getting access to these wavelengths that are difficult from the ground is really important for just having a complete knowledge of, from like 2000 Kelvin down to 250 Kelvin, what molecules should appear at what wavelengths. Just having that baseline knowledge is important for validating our atmospheric models and understanding what we know. Okay, so I'm gonna stop here and just take some notes, or take notes. Stop for any other questions about this project before I move on. All right, I will on it.
Question about how come that Mary was here?
I don't know. I think as like someone who's just a user, I know Miri had a lot of like baseline tools. Like you can actually do detector level modeling and add a source and had a pipeline set up. And so I'm not sure if that infrastructure was there for NearSpec, but I'm not on the behind the scenes, but I think at least from my experience, I think they're just super busy, I think, in terms of, and we're still doing calibrations. And so I guess it's a part of just being patient. I would say, I know there's a lot of frustration with observers about like, oh, why doesn't like the help desk do this? But at least every time I've approached with like this issue, they've been understanding, and they're busy like us as well. Yeah. Jane?
Explain more about why it's important that it's out of chemical equilibrium.
So, okay, this is one, I think it's important because the mixing doesn't just affect methane, it also affects other molecules that we may not be able to see. So it's important, if you know there's atmospheric mixing, you can actually infer what the other abundances should be given if this thing is true. And so I'll talk about this a little bit later. So we know methane is not the only disequilibrium molecule. There are things like phosphane, germane that happen in Saturn and Jupiter that we have not seen in brown dwarfs. And so that tells us that there is some issue with how do we treat these molecules. And we can't just say, oh, it has an underabundance. We need to know why it's not there. Yeah. And okay. Did I see another hand? Okay. Okay, so this is probably the last in-band ground-based project you'll ever see, given that JWST exists. So, I talked a little bit about, why is that 3 to 5 micron range so important? Cold gas giants are easy to detect at this wavelength regime, and we can study things like late T dwarfs and Y dwarfs to kind of understand what type of atmospheric chemistry and physics do we expect to see in the future. So this is basically, this project is just getting an in-band spectral sequence of brown dwarfs that are like 750 Kelvin down to about 250 Kelvin, and then I'm including Jupiter in this sample. So this is a spectrum of WiseWave 55. It's a brown dwarf that's 250 Kelvin, plotted in black with the error bars, and in blue I have a spectrum of Jupiter. And so WiseWave 55 and Jupiter are only 100 Kelvin apart, but have very different spectral features in the mid-infrared. So this absorption feature here in Jupiter is due to phosphine. And WSOE 55 basically only has water across its atmosphere. So we wanted to go beyond this work and understand, okay, from below 700 Kelvin, is the effective temperature the only thing affecting the way these atmospheres look, or is it some other atmospheric property that we aren't properly accounting for? And so that's what I did. So this was a 50-hour program at Gemini North. These are just the objects I had are in the sample. So these top two, Gliese 570D and 2MASS 0415, already had their data taken with Gemini NIRI and Akari. Akari is a space-based satellite that took mid-infrared spectra through JAXA. And then WSOE 55 was published in 2016 by my advisor, and then we've been taking data on Jupiter forever. So I had to include these 4 objects, and I had to spend 50 hours just to get 4 objects. And I filled in this gap from 700 Kelvin to 250 Kelvin. Okay. So I'm gonna talk a little bit about the observational setup because it was really hard. So we use the low resolution mode at an R of 1000, but because the background is so high, we bend it down to basically like an R of 100 or so. And the coverage was from 4.6 microns to 5.1. And because the sky background is so high, we have to utilize really short coads to avoid non-linearity on the detector. And we had to basically, you can't take a spectrum in the mid-infrared unless like the air mass is just right. There's no, like, there has to be very little precipitable water vapor and good, basically good conditions to take a spectrum. Okay, all of the targets that I showed have a J-band magnitude of like 20 or less. So we basically had to use it. We had to utilize blind offsetting to get a spectrum. And so typically we have an offset star here, and then we have accounting for like the proper motion of the object. We have a prediction of where it should be. And then we put the slit on the offset star, put it on the circle, and you integrate for 2 hours and you hope it's there. So we had to utilize an ABBA nod pattern to, remove some of the sky subtraction. And we have to take calibrator spectra every 2 hours of observation. We have to take a calibrator at the beginning and the end because, okay, I personally have not taken a near infrared spectrum, but I've seen some people do it. And some of you take a calibrator at the beginning of the night and like, it's all good, but no, that does not apply here. Because you can have as big as like 10% difference on your telluric calibrations if it's not like contemporaneous with the data. Okay, so this is what theory predicted at equilibrium. This is the same bandpass as 4.5 to 5.1 microns. From 600 to 200 Kelvin, the only thing at equilibrium that changes is just the amount of water absorption, and basically the slant changes a bit. But that is not what we saw. Okay, so these are all of our brown dwarfs plotted from hottest, hot to cold, cold to coldest. And so as you can see, there isn't like this slant here, there is a peak here. This one's basically flat, there's no slant. This is flat, and you can argue it gets brighter at redder wavelengths. And this one has a very nice, obvious CO feature across the M band. This one is not slanted down, it increases with wavelength. And then WSOE 55, I re-reduced this data to prove that my pipeline worked. And it still looks the same with mainly water. And then Jupiter has phosphine and water as well. So none of these objects follow basically the slight change in slope just due to water. So we have to figure out what's that one thing we can crank on the models that can best model most of these spectra. And so that thing we changed was the carbon monoxide abundance. So, oh, my bad. This is just a plot showing that the equilibrium models don't match the data. I think the worst example is this one where it's crisscrossed with the equilibrium model, and most of them have excess flux at equilibrium compared to the actual data. In all cases, even WSOE 55, where we previously just attributed to water. So for each brown dwarf, we just changed the carbon monoxide abundance until it matched the spectra. So I'm just gonna flip back and forth so you can see how it improved the fits. So for all the objects in our sample, if you add carbon monoxide, you get a slightly better fit to the spectrum. And Jupiter's not included here because I have not tried to apply a brown dwarf model to Jupiter, but at very high resolution, Jupiter also has carbon monoxide features as well. And so what's important is not only just the feature matching the spectra, but there is a trend with the amount of abundance required to match it with the effective temperature. So the hottest brown dwarfs take the most, I measure abundance in mole fractions. So the hottest one you have like 10 to the 4, whereas Y0855, you have like a mole fraction of like 10 to the -7. So in this temperature range, you can have like a factor of 3 difference in carbon monoxide abundance. Okay, so I was not going to try to model a 1 to 20 micron spectrum of a brown dwarf, but we can do this with M-band data and near-infrared spectra of Y dwarfs. So with this, we actually tried to figure out how much atmospheric mixing, how can you quantify that based on the amount of measured CO abundance you have in the spectrum. So I actually have a schematic here just so you can visualize what I'm talking about a bit. So this plot was done by Sognick Mukherjee. This is for a proposal we put in. This is like top to bottom of a brown dwarf atmosphere. These molecules are methane. These molecules are carbon monoxide. This dashed line is kind of the photosphere where your spectra are sensitive to. And this is the case where there's no atmospheric mixing, where KZZ, that's how we quantify atmospheric mixing, is the eddy diffusion coefficient. And this is a case in equilibrium where KZZ is equal to 0. Now, if you have a little bit of mixing where KZZ is very low, you have some carbon monoxide molecules getting up to the upper atmosphere, but it's still methane dominated. And then in the high KZZ regime, you're basically all CO dominated, and there's just a little bit of methane that's hard to detect. So that's kind of what we're measuring with our models. Okay. So I'm gonna try to go through this step by step. So for every brown dwarf, we have a carbon monoxide value. Based on our atmospheric models, we can estimate a KZZ value associated with that carbon monoxide abundance. And since KZZ is dependent on surface gravity, there is a distribution of possible KZZs for each brown dwarf. There is not a distribution for Jupiter because we know the mass of Jupiter. So for every brown dwarf, we have the KZZ plotted versus effective temperature. And oh yeah, I guess I'll start with just the trend of the data itself. So even though the very warm brown dwarfs have a lot of carbon monoxide, they require a lot less effective mixing, they require a lot less atmospheric mixing to keep up that high abundance, whereas these low effective temperature brown dwarfs and also Jupiter have to mix really fast just to maintain their low abundance values of carbon monoxide. Now, the next thing, this is my favorite part of the paper. These dashed lines are the theoretical maximum if all of the heat of the object is contributing to convection in the brown dwarf. What is the expected mixing you should get? Y0855 and Jupiter are mixing within their theoretical upper limits, whereas these brown dwarfs are a lot sluggish compared to that value. And so this may hint at the fact that M dwarfs, brown dwarfs are not completely convective. They have some radiative zones. And so there may be portions of the pressure temperature profile where the gas is not efficiently mixing. And so it results in a lower effective mixing measured in the object. And so I actually put in the JWST cycle 2 proposal to not just like say, is there one KZZ value for the entire object? What is that mixing profile look like? And understanding this is not just important for abundances. It tells you what kind of clouds can settle out in the atmosphere. It also has implications for the other apparent chemistry of the object. So this is just like the start of what JWST can answer in the future with high fidelity data. Okay. So in summary, I don't know why I left that there, but this is just highlighting the 2 regions of the color magnitude diagram that I focus on. I focus on this region where we know directly imaged exoplanets exist and we're studying their analogs. And so with JWST, we know VHS 1256b is a very dynamic object with cloud features and also its apparent chemistry is influenced by disequilibrium chemistry. And JWST has its potential to understand these atmospheric properties for other brown dwarfs as well. And in this region where we haven't detected directly imaged exoplanets just yet, we know that the existing late T and wide dwarf population have carbon monoxide absorption. These two populations of brown dwarfs have carbon monoxide features, which tells them that they're also have strong mixing in their atmospheres, which also influences the atmospheric chemistry. And lastly, this is like by pure chance. I wasn't expecting this when the proposals went in, but all of these atmospheres are influenced by atmospheric mixing. It's a very fundamental property we need to include when modeling any gas giant planet or brown dwarf in the future. And thank you for your time, and I'll take any questions.
All right. First.
Okay, as someone who doesn't work on abundances or stars, or let alone brown dwarfs or exoplanets, I was struck though with the VHS 1256b. At the beginning you showed a picture where it's connected to a companion that's I believe an M star, I think you said.
Yes, and
I know it's hard to get abundance constraints from M stars, but you've got now data that show that there are silicate clouds in your brown dwarf.
yeah.
Are there constraints on any of the refractory abundances like silicon or others from the M star itself, so that you know whether there's something commensurate or appropriate about, the excess of silicates that you've got in this source?
That's a good question. I don't think the same effort has been put into characterizing the host stars of this planet. So like M dwarfs also have CO features, and you can get really good high resolution data. And so I'm not sure if like the abundance budget has been done on the host companions and that's been compared, but I think that's a really good question to answer.
Thank you.
So maybe following up in the sense that like this one has a companion. And so just wondering, I guess in planets in the solar system, or kind of moons around planets in the solar system, I think that some of the kind of tides can speed up kind of internal processes. So I was just wondering whether any of the mixing that you're seeing in the measuring really with the CO abundance in the brown dwarfs kind of if their larger scale environment can be affecting that, or do they have companions that could kind of trigger some of that?
That's a good question. I think that's a big unknown. Like if something was really close to another body and they actually like interact. I'm not sure we can answer that question really well just now. And I would say that type of question shows a shortcoming of like, what are we sensitive to in the atmosphere? So right now, planets and brown dwarfs form probably differently, but right now we don't have that spectroscopic signature to tell you how they form differently. And so if there is something that tells us, if we can directly link some internal process to how we see the upper atmosphere, I think that would be a game changer for the field. Yeah, and people think it's deuterium, but we have to spend the time to measure that.
Online.
Tony's got a question, so you just unmute.
Okay, yeah, Tony, if you want to unmute.
Yeah, I just had two quick questions. I mean, the case ZZ, I wasn't sure. I didn't have a good sense of what those values are. I guess the natural scale I would think of is the speed of sound times the scale height.
Yeah.
For a diffusion process. So I was just wondering, is this in that same ballpark? Is it a lot bigger or smaller, which maybe suggests some sort of larger scale mixing like Anna was suggesting?
That's a good question. I think, unfortunately, I don't have like the exact number for like the speed of sound, I guess, but on Earth, just in our upper atmosphere, this value can change as much as like 10 to the 4 to like 10 to the 11. So it's not like, I think it's a very unknown parameter, but it can be very large on a planetary body. But I would have to do the math to get back to you on like, regarding like, sound and things like that.
Yeah. And then the other quick question is just what's the range of orbital periods that your brown dwarfs are in that are with parent stars?
So for VHS 1256b, I believe it's on the order of like thousands of years because it's so far, but most of the colder brown dwarfs that I was talking about are isolated, but Gliese 570d, that's also a long orbital period object as well, but I'm not sure if we have seen the motion from the orbit.
Okay, that makes sense. Thank you.
Any other questions? Yes.
Thank you. Great talk. I'm no biochemist. I'm hardly an astrophysicist. But if you had a pristine, perfect SCD,
Yeah.
what collection of, you mentioned ozone, for instance, a biosignature. I can also imagine methane from a primordial sea. What collection of features would be a smoking gun of biosignatures? And what statistics do you expect with JWST for such detections?
That's a good question. I don't have the expertise to answer, like, you know, if you see this and you don't see this, is that mean it's from life? But I think the question we need to ask is like, if you only have X amount of hours in 10 years, you know, what can you reasonably tell between an Earth-like planet that does have life and doesn't have life? Or can you tell the difference between Earth and Venus? I'm not sure we can answer, is this ozone feature produced by life with just one observation though? But I know less about the chemistry aspect of it. Yeah.
Anything else? Oh, yes.
So you mentioned that MIRI MRS channel 4 was the most difficult and least sensitive, and you had a dot there rather than a spectrum. Is it recoverable, or is it just too hard given the faintness of the object? I guess I'm trying to know not just this object, but in general, how much channel 3 and channel 4 are going to push the field forward versus most of the results are going to be less than 10 microns.
That's a good question. So some of the issues with this project is like, you know, how do you get an adequate background from MIRI? So one thing, we planned a background observation but didn't use it. So we were using apertures from within the same observation as the brown dwarf. And so I think there's definitely growth in like, how do you get an adequate background subtraction for MIRI to understand what is that detection limit for the object. But I don't know, like, even like just with theory or what we've seen in the solar system, I don't know what specific feature you would track there. I do know that so for Jupiter and Saturn, you have these emission lines from hydrocarbons. And so I think this is not my work, but you can do some cross-correlation analysis to understand what are some complex molecules you see at those far wavelengths and what signal to noise you need to retrieve those. And so I think that is, I think that's something that needs to be explored, but I am worried the community is just going to give up on MIRI and just say, let me just take this 1 to 5 micron spectrum. But yeah.
All right, any last questions? All right, let's thank Brittany.